We'll begin with our homework problem associated with subgradient, and then look at the calculus of subgradients, necessary and sufficient condition for optimization with and without convexity. That's how I'll progress, and I'll leave you with some homework problem which will apply some of the concepts taught today for minimization. So recall this homework problem where you were to basically figure out we have to figure out if the subgradient is guaranteed to exist at each point in a domain for a convex function. So any assessment, any conclusion you have from your end? Yes? Even if it's not differentiable. And what's your intuition? So answer seems to be yes. What's your intuition? Will be some? We can find a lot of okay. Yeah, so yeah, and the solution seems to be in the line of basically showing the following, right? So homework 1, if the function is differentiable, is convex. I'm not going to do detailed proof here, but the idea. Then what we know for sure is that the gradient of f is an element of the subdifferential of f. By definition of gradient, right? And if it's not differentiable, then we'll have a slightly interesting but related property that the gradient is kind of the normal to the tangential plane in the direction of increasing level curves of the function. Okay, so if you look at increasing level curves of the function, if not, so the intuition is that the gradient points in direction of increasing level curves. So it's a normal to the tangential plane. Now the notion of a tangential plane may not be unique. That's what we'll see. But there exists some tangential plane and gradient is that normal. But if it's not, if not, then this gradient is still, or the subgradient is playing the role of the gradient. Okay, so you can always have increasing level curves, whether it's differentiable or not. You can always plot, normals or points that, vectors that point in the direction of increasing values. So intuition is that that should be possible. But what has that got to do with convexity? That's the key, right? So a lot of the convexity is coming because of, so remember convex sets. What did we have associated with convex sets? At every point, we had a notion of a supporting hyperplane for convex set. Did that require the convex set to be cornerless, smooth on the boundary? Nothing, right? So if not, intuition is gradient, subgradient should point in direction of increasing values of level curves and should be perpendicular to supporting hyperplanes. At each such point. On the level curve. This is the key here. This is where convexity is coming. Should be perpendicular to the supporting hyperplane. Make sure you get this intuition. Okay. You don't have this privilege if it's not convex. Sublevel sets, the level curves, the sublevel sets are convex when the function is convex. Right? It may be convex even if it's not. That's why we are quasi-convex. So quasi-convex functions possibly could have subgradients also. In fact, they have something called quasi-gradients. Okay. But if it's a convex function, this seems to be very intuitive. This part in pink, is this clear? Okay. So the same intuition is being carried forward. So look at this. The part in red is like the gradient, right? Pointing. So gradient is not the tangent. Huh? Gradient defies the tangent. Please be clear. At the end of last class, some people came and asked me. Okay. This gradient is pointing orthogonal to the level curve. Sorry, I mean, is pointing increasing values of level curve orthogonal to the tangent. So there's a tangential plane here. And maybe I'll put a pink, use a pink color here to be consistent with it. This is that supporting hyperplane and its perpendicular is the subgradient. Now, if you look at the in the higher dimensional space of the function value, then this supporting hyperplane is supporting the epigraph of the function, right? The graph lying above the function. That's what you see there, epigraph, for the blue tangential hyperplane. And the normal to that is the gradient. Is this clear? Gradient is not tangential to the function. It's normal to the tangent. So this is the intuition. What we'll have show a proof. We'll just show a glance at. Basically, says that gradient is always a subset of subdifferential, and if it's a differentiable convex function, we'll show that any subgradient which lies in the subdifferential must become the gradient if the function is differentiable. That's the second part. Okay. The first part, the intuition is clear, right? Okay. Okay, so keep always, I keep showing this. This is our mascot. This is our kind of, the impression we should carry in our mind of the notion of subgradient, the one in which is tangential, right? Sorry, one which is normal to the tangent. Okay, so now we'll move on to, I'll say that we'll move from subgradient calculus to local and global minimum, and then sufficient subgradient condition for global minimum. I think we'll probably only hit until this point today, no matter how fast I go. Okay, so just again recap this. If a convex function is differentiable at point x, then what would you expect the subgradient to be? Yes, subgradient will be exactly the gradient. Okay, so just for phi is greater than or equal to x plus h. So now customarily you can put an hx transpose just to create an impression in your mind that is h is a function of x. You can put in bracket and x also, but it's not really a function in the sense of a gradient. You can't compute it by taking partial derivatives. So you can put a subscript hx here if you want. Though most often in practice you don't do that. Assume it is a function, h is in terms of x. And this should be for all y. Okay. So the statement, just to complete the statement here, if F is convex, convex S is differentiable, then you'd have Hx must be the same as gradient of f at x. Okay, that's the completion of the statement by virtue of the homework. Now, just to give an idea why that may not be the case otherwise, right? So this function may make sense, but let's look at this. If the function is not differentiable, right? This hinge loss, and you see at this point what happens at this point t where it's not differentiable, convex but not differentiable. So you can have lots of subgradients, lots of normals to the tangent because there are many tangents. All these are tangents, right? You see this entire there's a cone here. The shape part shaded in pink is a cone on both sides, right? And that is basically a convex hull. Basically, it's a convex combination of multiple tangential hyperplanes. So in as much as this, right, this is a convex combination of multiple tangential hyperplanes, the subgradient is also a convex combination of or a convex hull of those extreme cases. Okay. So if I have this, so I take the tangent here, tangent here. These are all my, this is a convex hull. Convex hull of the extremes. Likewise, these take the this is also convex hull of the tangents. Okay. So you can imagine, right? If the function has exactly one tangential hyperplane, then have one normal, which is the one single gradient. It has a unique subgradient at that point, which is the okay. So this is a case where you have. So let's take this example. This example is interesting because this curve, which I just showed you, right? This curve, right? If you imagine, this is basically having only one kink, right? And this is because it's a max of two functions. Okay. So let's take the case when the function is a convex function, which is a max of two convex functions, right? Max of two convex functions is convex. What happens here? Even in this case, everywhere else in the green region here or the pink region here, where the max is f1 or f2 alone, there's a single tangent and a single gradient. The problem is only at this point, right? And what will happen here? Well, you'll again have this tangential, a cone basically, a tangent cone and a normal cone. The normal cone is basically the subgradient, and the tangent cone is, right, it doesn't have a name. In fact, the normal cone is called a subdifferential. It's a combination of all, it's a space of all possible gradients is called subgradients is called subdifferential. We'll see that. This cone, yeah, this cone, right? This cone is a space of all subgradients. And this is called subdifferential. That's the name. We'll see that. It's a space of all subgradients. Okay, so what's the formal proof? All this I've given intuition, single gradient, blah, blah, blah. Let's just see that the gradient indeed coincides with a subgradient for a differentiable function, or for a differentiable function, the subdifferential is a singleton set. So this proof is there in my very detailed notes from my convex optimization course. So I'm not going over it. But the key idea here is as follows. The proof I provide is that if the function is differentiable, then the first point is the gradient belongs to the subdifferential. Say gradient is a subgradient by definition of by this definition of convexity, right? Inequality holds. Now let H be a point in the subdifferential. Let's say that is not the gradient. That's the typical trick. You say, well, H is a point which is not the subgradient, and I'll show it turns out to be the subgradient. H is a point which is not the gradient, and I'll show that it turns out to be the gradient. Okay. So now because f is differentiable, then I write down its directional derivative along y minus x. The directional derivative. And then I use limits. What's the meaning of a directional derivative? Right. Then I wrote basically I write down by first principles, use limits. And then little bit of algebraic manipulation. A little bit of algebraic manipulation, and basically I can show that, yeah, so this is important. So H minus gradient fx should be less than epsilon for any value of epsilon. For any epsilon greater than 0, this is the trick. Trick is do all that, cancel out common terms, and show that H minus, if H is a valid subgradient, then H minus the gradient of f at x, its norm should be less than epsilon for any epsilon greater than 0. Basically means that this difference must be 0. Right? So that's the trick. You somehow get rid of epsilon everywhere else except in this upper bound and show that it should just go to 0. Okay. So therefore H must be H must be the gradient alone, no other point. So I have given the intuition here already. Okay. By the way, you may have also other questions. What about convexity and continuity? Right? Is the convex function always continuous? Because we looked at the convex set, the epigraph, and all that, and we found some interesting properties. You don't expect disconnectedness so much in the convex sets. Can we expect discontinuity in the convex function? So yeah, this is interesting. There are continuous functions which are nowhere differentiable. Convex functions are typically not pathological. So convex function is differentiable almost everywhere. That's an interesting point. So the set of points where it's hello, not audible. Set of points where it is not differentiable, its measure goes to 0. So it's pretty much everywhere differentiable. So on the other hand, if f is a continuous function, if domain of f is open, then f is actually continuous. So continuity generally holds if the domain is open. Okay. Differentiability, there's a bit of slackness. So it's possible not to be differentiable in some places, but actually almost everywhere it's differentiable. Okay, there's a small detour. Okay, now let's look at subgradients and convexity a little bit more detail. So as I said, there's a notion of subdifferential, which is just a space of all subgradients. Okay, I'm not going to write that again, but the subdifferential is denoted by partial f, the set. Yes, a function, as I said, if the domain is open, it's going to be and convex. The function will be continuous. Now it's possible that the domain is not, so you can consider a domain which is not open. right? A domain which is not open, it's possible at kind of the boundary points. The function is convex but not continuous. But the interior will expect it to be continuous. Interior of that domain. Is that clear? Domain open basically means that when you consider it the interior of of the domain which happens to be not open. Okay. So now we're going to look at calculus. Okay, subgradients and convexity, but we're going to look at a little bit of calculus in the sense how do you compose subgradients. So let's, before I show anything further, let's take the intuition again. If I have two curves, sorry, I show this and two curves like before. This is F1 convex. F1 is convex. F2 is convex. So let's say I'm looking at max. Okay, F is max of F1 and F2. So now imagine I put in an F1 here, right? At a point X. Let's say this is the point X. Hx for F1, Hx for F2. Right? So you'll have F1y greater than or equal to F1x plus K. I'll just put an F2 here. Let's say this is F1. This is H1. Okay. Then I'll have H2x transpose. So you see, I have a subgradient H1x for F1 and I have a H2x for F2. You see these two normals. The subgradient is normal, right? So if I want to now show a subgradient for max of F1 comma F2 applied to y, I need a similar inequality, right? Max of F1 comma F2 x. So max of F1 comma F2 y should be greater than or equal to max of F1 comma F2 x plus something new, right? I'll call it H new transpose at x point x, y minus x for all y. Right? This is what I want to derive. So I want to know what is this H new x? How can I write it in terms of H? You understand the question? What is your hunch? I gave a hint already a couple of times. How do you think you can compose your H new x in terms of H1 and H2? Sorry? Supporting vectors. What did I do some time back when I had these two normals? I had these two. What did I do? I shaded this region, right? I said convex hull, right? So what would convex hull mean? H nu x could be in the convex hull of H1 x and H2 x. Sorry, let me write it properly. H nu x it should belong to the convex hull of H1x and H2x. The shaded region, this cone that will extend infinitely down. Right, and that is my H nu x. Is that clear? The intuition is clear, right? I want to, I can move around in that space. Those are basically my boundaries. H1 and X and H2x. Okay, so that's how we come up with. So I'm not going to do in as much details all the other properties. This is one property, very intuitive. Pointwise maximum. If fx is max of m convex functions, not just two, here we consider two, but m convex functions, then the subdifferential of f is basically the convex hull of what? Convex hull of the subdifferentials of the individual fi's. But at those points where the function values match. See, as long as I was in this space, like in this space, what is the subdifferential of the composite function f? It is basically the gradient of f1. In this space, what is the subdifferential of f? Gradient of f2, right? The problem is where they match, the max coincide. So that's what we are doing here. Okay. We are saying fi x equals fx for all I, all those indices, functions where the indices match. Okay, so here I've tried to show this. Look at all the I where ix equal fx. So this is, in this case, I again shown the same f1, f2. But all those which where they match, only those you have to consider the subdifferential. If one of them is only the max, no problem, it's gradient. So this definition is general. Okay. So while I wrote a little bit intuitively there, the formal statement or formal expression here is the partial of f is the convex hull of the union over all indices I, such that fix equals fx of the partial of fix. Is it clear? The partial. So all of you will have to write descent algorithms, right? If you write descent, you need to know how to compose for max. It's very handy. Right. So all these functions for which the function values match or coincide with fx, they're called active. They're the active functions. Yes. Yes. Correct. If there's only one, it will be gradient basically. I mean, if it's differentiable, obviously it may not be differentiable. Again, you'll have to. So each fi could itself be another max. It could be another non-differentiable function. We don't know. So we are saying, well, look at the subdifferential of fi. If fi is the max, only max. You mean fi itself, no? If the partial of the subdifferential of fi itself is not a, yeah, that's what I'm saying. So it itself may, so the subdifferential of fi itself may involve another union. So your question is about where it's not differentiable. Mm-hmm. This one. Uh-huh. Here. Oh, so let me try and draw a curve which might you're maybe referring to. Okay, I'm going to erase this. So are you referring to, so let's say like this. So function is decreasing, then becomes flat and then increasing again. Why? Because it's a max of some three functions. The first function is this one, the second is a flat function, the third is another convex function. So in this case, what will happen? Sorry? It's another function. There'll be two different cones. So there'll be one cone here. There'll be another cone here. And what will be the gradient at intermediate points? 0. Okay, no rate of change. Okay. Well, I mean, I can't say 0. See, we are 0. And, it could be an affine function. It could be tilted slightly. I don't know. It could be A transpose X, in which case the gradient is A, small A transpose X. So yeah, just let's say this is best to keep it generic. Just E, constant. Okay, but I think this picture should be illustrative enough of the generic case now. Okay, I have just done this once more here. So you have F1, F2, and here in all these regions you're looking only at the partial, the subdifferential of F1. In this region you have F2. There's only one active function, so you're looking at the subdifferential of F2. Whereas at this point you're looking at active functions which are both F1 and F2, and therefore you will consider the two cases, which is the subdifferential of F1, which is this one, the subdifferential of F2, which is kind of this one, and you'll also consider all the convex combinations of the convex hull. Okay. Now let's look at a couple more others. I'm not going to spend as much time on others. Okay, so you can also have general point-wise maximum. Yeah. The boundaries of this, right? Now, as I said, F1 itself could be a max of some functions. F1 itself could be a composition. We'll see more compositions. We have only seen max. What are other compositions you remember? What all did we consider? Okay, basically you can have a log. So concave, convex combinations, but then you have increasing, non-decreasing, non-increasing kind of conditions under which convexity is preserved, right? You can have those compositions. Linear, obviously linear the simplest. Log is another transformation. Non-negative weighted sum. We'll see some more. And so there are many other transformations possible. So F1, F2 may not be as trivial. But yes, the subdifferential of F1 is what I'm referring to. To me, this boundary is a subdifferential of F1. This boundary is a subdifferential of F2. This is clear. That's it. Any other questions? So please ask. Good that you're asking so many questions. Okay. So you have a notion of a general pointwise maximum, right? Where you're not looking at an index which is finite. So what's an example of this? Do you recall last class we did this? What is a generalization of this pointwise maximum? Yes, anyone recalls? Matrix induced vector norm. Sorry, vector induced matrix norm. So if I have a matrix A and I want to compute its norm with respect to vector norm n, how did I define this to be? Supremum over, yes, x not equal to 0 of something divided by something, right? Sorry, exponential. Sorry, norm, right? So we had the norm of ax we have norm of x. You recall this example? We got some norms because of this. Which norm did we get because of this? The max row, the max column. Infinity norms, we right? Infinity and well-one norm. Here's row and column and etc. Right? And we also found one more, right? What is that? Spectral norm. Spectral norm is under the n becoming 2. When n is 2, what do you get? The max of all the singular values. Right? Max of singular values is spectral norm. Okay, so let's just recap. So this was, so under this what happens? Let's see under some regularity conditions which are not fairly generic. The subdifferential is the closure of the convex hull over now all the unions. Same thing, same idea, but there's a closure. The only addition is a closure. Otherwise, it's the convex hull of all the unions of all those points, the active points, the active functions, functions on which the max coincides. Okay. The only thing is closure. Closure because you may be dealing with an infinite number of such vectors, right? So if you're looking at convex hull, you want to make sure that you also cover the boundaries. That's the only difference. right? You can recall this. We had talked about this. The slide you recall. I talked about n equals 1 norm, which basically corresponds to column with maximum 1 norm, and n equals infinity norm corresponds to row with maximum 1 norm, right? How will you compute the subdifferential for these? So it's not very difficult. If you have basically consider a row or a column with the maximum 1 norm, the subdifferential will involve that row, particular row, right? But there could be, now what's the point? What is the support notion here? See, is support. So support will involve multiple columns which have the same 1 norm. It's possible that multiple columns have the same 1 norm, or multiple rows have the same 1 norm, right? Then you will consider those columns or those rows and their convex combination. That's basically it. Okay. You understand what I'm saying here? Here, when you have the support fs x equals fx, consider all those rows which have the same 1 norm, or all those rows which have the same columns which have the same 1 norm, right? Rows in the case of infinity norm n equals infinity, and columns in the case of n equals 1. Okay. So yeah, they should be able to do these. I mean, I don't want to spend all the time here. Now let's look at a special case. Okay, spend little time on this. What is the subgradient of 1 norm of x? Simple use case. Can I write it in terms of this max or supremum? Open your notes. You should write this. Subgradients of the 1 norm of x. Can you write the 1 norm of x as a max over multiple functions, a supremum or a max? How is it? Sorry. Okay, minus x. Can I say a minus? So s equals -1 comma +1. A vector s which is just of -1s and 1s. All possible combinations. How many such vectors will exist? Infinite. -1 and +1. That's it. Yeah, two power and such vectors. So max over what? Max over this s of max of what? Now the rest you should complete. One norm of x will be max of what? Yes. I won't proceed till someone suggests this. This is very simple. Too simple to miss. Very simple dot product. What is it? Sorry? Sorry? Norm of x. But I don't want to again get a norm. Na? One norm of x itself is not differentiable. I don't want to define again. Something to do with s and x. Huh? Max of s transpose x. So what's the big deal? Take all possible. So, right, what are we saying? Basically, we are saying max over all s of this s of summation over I xi si. One norm is basically sum of absolute values, right? Sum of all absolute values of xi's You'll get the absolute value if you consider -1 plus 1, whichever gives the best max value. Is this clear? Please make sure this is very simple. Sorry? You're just projecting X. Yeah, true. Oh, there's space of S's. But this is not really vector space, by the way. This is not a vector space. This is combinatorial number of S. So projection, not vector projection or projection on a vector space, because it's not a vector space. Right? You understand this? I used V here instead of X, but this is the same. Max over V in -1 to +1 V transpose X, which is max of, this is basically, right, max of x1 plus x2 plus x3 plus x4, comma, x plus x1 minus x2 plus x3 plus x4, comma, x minus x1 plus x2 plus x3 plus x4, comma, minus x1 minus x2 minus x3 plus x4, and so on, right? One of them is going to give you absolute value, some of absolute values. Is clear? Now, what next? How is this expression helping me find the subgradient? Sorry? Same form, right? So, will be what? Subgradient of x1 will be what? Exactly what I wrote there. Convex hull of so there could be multiple linear combinations which you can give you the same value. Is that possible? So let's say, I'll show some examples, right? So if I have x is -1 plus 1, that's simple vector. X is -1 plus 1. What are the values of S that can give me the norm? Sorry, let me take slightly. This is very simple. -1, 0, 1. Which values of S will give me one norm? -1. So S could be -1. It should be the same sign. The third component is 1. What about the intermediate one? You see now why convex hull is important, right? The second component is a closed interval, -1 comma +1. It can be any value, right? Or it can be -1 slash +1, whatever you want to say. Okay, so x1 norm, one norm is the max of x transpose, which is a pointwise maximum of 2n functions. Okay, and you can see that 2 raised to n configurations of S. And the problem is, of course, going to be those regions like here or here, right? Or here, these yellow regions. Those are the regions where there could be a zeros because multiple of them coincide. Right? So let S star be the set of S such that for each S and S star, the value of X transpose is the same max value. Right? So S star is basically all those which give you the same max value here, because that's where this linear function and this linear function have the same max. Whereas this doesn't. This is also a linear function, but this has no role to play here. This linear function has no role to play at this point. Likewise, this linear function, the segment of a linear function, this linear function has no role to play again at this point. Understand? Okay, so there's a convex hull of the union of all the S star, right? Those yellow points. S star such that the value of X transpose is the same max value. And I give this example. If you have X equals 0, if especially there's a 0 point, that's when you have multiple such S. All of them will coincide. Right? So in this case, S transpose X is 6 for at least two such vectors. So that is S star X. Okay. So S star X. You just say S in this S star X. Of what? Now you look at partial derivative. Okay, so partial derivative of sorry, not partial derivative. What I meant is subdifferential. Subdifferential of S transpose X. Right? Which is nothing but what is the subdifferential of S transpose X? Is S, na? It's basically convex hull over union of S in S star X of just the S. That's it. S transpose X is subdifferential is S because it's differentiable, particular S transpose X. So that's what you get. Understood? So if you want to depict this again, right? This is how it look like. This is a convex hull. There are two S's which give you the max. Both the S's you take the convex hull. And that region S star X is basically defined by these boundaries. This was one boundary in S star X, and this is the other boundary in S star X. This one, this green line. Oh, is that clear? Okay, so we have seen the example of one such property in the calculus. Now I want you guys to guess. Just guess. Oh, Max, we did this, right? For linear transformation, what will happen? A transpose X. If I take it subdifferential, or A transpose F. Okay. A transpose X, F of A transpose X. Right? Then what will happen to A? It will basically, yes. Okay, so look at this. If gx is f of ax plus b, then the partial derivative of subdifferential of g at x, the a will come out with a transpose. If there's an ax, it will come out with a transpose outside. If it is a transpose x, it will be a. So whatever the multiplicand is, matrix is inside, will come out with a transpose. Okay. Again, you can again show it by first principles. But for gradients, you know this. Right? This holds for gradients. If you have a factor and kind of extends from here, right? Scaling itself. Subdifferential of AF is A times the subdifferential of F. Similarly, the subdifferential of F of AX is the subdifferential, is A transpose times the subdifferential of F at the same point. So no difference. Instead of multiplying by a scalar here you have multiplication by the transpose of the matrix. I think I told you a very simple rule of thumb, right? Whatever you want to even eliminate a gradient, bring it as a transpose in the pre-multiplication for that matrix, for that vector, right? A transpose X, small a transpose X. The A transpose will kind of get cancelled when you do a gradient computation. Okay, now I'm going to take that so others are simple, right? Addition is very simple. Subdifferential of F1 plus F2 is subdifferential of F1 plus subdifferential of F2. Very much like gradient, no difference at all. The first three properties are clear to everyone. So if you want, we can just write them down, but yeah, you find it useful. Let's write them down. Okay, so we saw this first one, which is the max, and then the simple one. Sorry, I didn't like that. Now let's get a fourth property. Three properties are simple. The fourth property is interesting. Norms, right? We have generally seen norms. So how do I compute the subdifferential of the pth norm? Right, p norm of x. It's a convex function, right? Some integral value of p. Sorry, some natural number p. P greater than 0. So it's interesting the way you can discover it. What's your intuition? What do you think? What happened with the one norm? Two norm. What's the derivative of two norm? You know, the square of the two norm. Two times. No, yeah. So we had to have some square root there. Raised to half. So it's 2 times x divided by norm x. Correct. So what you get basically is like something like raised to half minus half. So raised to minus half, right? What he's saying. So what do you think will happen here? From the hint you have just now seen. Sorry. H to the power 1 by p. Good that you was thinking. So you, you should hallucinate a bit and think about possible answers. Good. Any other thoughts? Okay, and a closed form expression is not always possible. We already saw with one norm. Okay, but it turns out that you can express this in the form of, okay, you know the Cauchy-Schwarz inequality. So this is giving you a generalization of Cauchy-Schwarz inequality. That's so. What's the Cauchy-Schwarz inequality? Yes, what's the Cauchy-Schwarz inequality? Sorry. No, don't go to F. Cauchy-Schwarz inequality, simple. X transpose Y, absolute value less than equal to absolute value of X. Sorry, norm of X. This is 2 norm of X. This square, sorry, right? Into 2 norm of this 2 norm. Can I write this differently? This is Cauchy-Schwarz. Can I write this Cauchy-Schwarz inequality differently? Is there another way of writing it? In terms of, say, max values? Okay, I'll come to think about it. Let me present the answer here, and you'll probably get the generalization of Cauchy-Schwarz. Okay, we'll write the Cauchy-Schwarz generalization. So I'm going to fill up some blanks. So I'm going to leave this empty for now. Let's move on. Sorry. Norm max of norm of x comma y square. No, very good attempt. Yes. Something along those lines, but that's not the exact answer. Yes. Okay. So let me. So it turns out that the P norm okay, sorry. So this is the subdifferential. I mean, oh, sorry. This is the, yeah, it's fine. This is fine. So the P norm can be written as, this is the Cauchy-Schwarz generalization. And now you think of how Cauchy-Schwarz can be written like this. The P norm of X is the max over ZQ transpose less than equal to 1 for Z transpose X, where Q is such that 1 upon P plus 1 upon Q is equal to 1. So we just saw the one norm of X. One norm of X can be written as max over S between -1 and +1. So you could think of that S -1 and +1 as, this is S, right? Of S transpose X, with the understanding that 1 upon P plus 1 upon Q is 1. So if P is 1, then what is Q? 0. Sorry, P is 1, then 1 upon Q should be 0. I mean, Q is infinity. So you look at the infinity norm. You look at the max value. That's another way of writing. I didn't do that here. You look at the max value of if P is 1, then you're looking at the max value of Z being less than or equal to 1 of Z transpose X. I mean, what we were doing with S is kind of take the max value only. You're saying 1 because the max value can only be 1. The question is how many of them you should put to +1, how many to -1. Max is in terms of the absolute value. So where to put the +1, where to put the -1 was the question in S, right? So you can figure out that when P equals 1, Q equals 1 exactly fits our previous story. When P is 2, what happens? P is 2. So now this is a generalization of Cauchy. When P is 2, right? Then what are we saying? The 2 norm of X is what? Max over. When P is 2, then Q is also 2, right? So there's a max over the 2 norm of Z less than or equal to 1 of Z transpose X. I'll use I use Z here. Z and X. Just to be consistent. You see the connection between these two? The Cauchy-Schwarz inequality, as you know, Z transpose X square is less than equal to 2 norm of Z into 2 norm of X. Here we are saying, which means an equality is attained when? When is the equality attained? When Z is a linear, a scaled version of X, right? They're proportional. Rather, if you put a norm constraint, they should be the same. Under a norm constraint, if Z and X are the same, then only the max is attained. Right? The max is attained when Z and X are in the same direction. So something around that. So now we are saying this max is attained of Z transpose X here. Sorry, did I make a mistake in the square here? Just a second. I don't know. It's okay, I think. This square is maybe wrong. The square is wrong. There's no square here. Get Z equal to X. But Z is less than norms. You're saying Z should be equal to X. Z should be the same direction as X. Why should it be equal to X? X may not be a unit norm vector, right? You want Z and X to be the same direction. You're right. So Z should be a scaled version of X. That's what you're saying. Exactly. So you understand from the Cauchy-Schwarz inequality, you're deriving a definition of 2 norm. So instead of saying equality, I'm saying is this correct? This implies that the 2 norm of X can be defined in terms of this inequality. This max. So this is interesting. Now what we are saying is not just for 2 norm, for any P norm, you can actually define the P norm itself to be a max over multiple dot products, but under certain constraint on the norm of Z, which is defined by the Q norm. Okay. So this is your first exposure to duality. Okay, so this is duality. Basically, you're saying if P is giving you one definition, P norm of X, what's the definition of a P norm otherwise? So like this for natural numbers, P is what? Summation I of absolute value of xi raised to P, the whole raised to 1 by P. This is one definition of P norm. What's the other definition of P norm we have just found? It is a max over the Q norm of Z being less than or equal to 1 of Z transpose X. Because it's max, I don't have to put absolute value. Right? In the Cauchy-Schwarz, there was an absolute value. You don't need that because it's max anyways. Right? So this is a duality. So there's a primal definition of the norm, P norm, and there's a dual definition. You see the dual definition is by eliminating. You're saying not this, not this, not this. It's max over Z transpose X. Max over multiple functions. The primal is giving you a constructive. The dual is giving an eliminative definition. It's eliminating many other dot products, only keeping one dot product. Right? We will not? Sorry. I'm saying for that definition, I use P to be a whole number. Yeah, that's true. We can similarly define Q norm. Even a similar expression can be derived. Raised to P, 1 upon P, both are defined, right? As long as P is greater than 0. Yes, yes. It works for non-integers. I was just giving integral as That's some as the case that you are sorry, natural numbers as the case you're used to. But you can use it for any real value. Any, let's say, let's talk about positive real value, right? Strictly positive real value. This is fine. Hmm. Sorry. We're trying to find out. We don't know how to calculate. If we don't know the value of p norm x, there'll be some. No, but let's assume that we know how to compute the p norm or the q norm. We are just giving two equivalent definitions. So we are not trying to find the alternative way because we don't know to compute. We are just saying this another definition, right? You can define a polyhedron, right, in terms of a polyhedron in terms of combination of all the corners, right? But you can also define a polyhedron as intersection of half spaces. Okay, so polyhedron you can define in two ways. If I give you these points, you'll say, oh, connect them. That is one definition. What's the other definition? I'll say, oh, a polyhedron is the same one. I'm just going to use the same one. A polyhedron is one which is at the intersection of multiple half spaces. The half space lying here, the half space lying here above, right? The half space lying below this guy, and finally, right? So there's put a white half space lying this. So that's one way. That's another way of defining intersection of multiple half spaces. You see the same thing is happening here. One is by the p norm definition. The other is through a q norm definition. Is that clear? Okay, so you can try and derive the subgradients, but I'm just recapping the Cauchy-Schwarz inequality, right? What we have done here is the Cauchy-Schwarz inequality, which can be written also can be used to derive the 2 norm of x in terms of max over z of z x transpose z, which I wrote on the board. And now we're just generalizing this to the p norm. Okay. And this, in fact, is related to another inequality called the Holder's inequality. Just like Cauchy-Schwarz inequality said, x transpose z absolute value is less than or equal to norm of 2 norm of x into 2 norm of z. Holder's inequality says x transpose z absolute value is less than or equal to the q norm of z into the p norm of x. Okay, so the Cauchy-Schwarz inequality. Now I'm generalizing. I'm saying not only this, z transpose. Okay, I'll give a different color. Z transpose x is less than or equal to, okay, instead of q and 2 norm, I'm saying the q norm of z into the p norm of x. And this is again giving me the p norm of x as the max over all z with q norm less than or equal to 1 of z transpose x. The generalization called the Holder's inequality. The original inequality was the Cauchy-Schwarz. Is clear? Now, based on this, can I write a partial derivative of the subdifferential of P norm of X? How will it look like? Should look very similar to this, right? It's a supremum. Now you'll not have this convex, you'll have a closure, right? Is what? Closure of convex hull of what? Union over, look at that definition. Yeah, Z transpose X. But differentiate Z transpose X. What will you get? Z. Union over all Z such that something should coincide, right? So less than equal to 1. Sorry. All Z such that Z transpose X is equal to the 2 norm of X. Now let's keep it more general here. So basically, it's a union over all Z such that Z transpose X is a P norm of X. Sorry. Sorry. This is but it's what Z? Z should have what property? Q norm less than equal to 1. Z transpose X should equal the P norm of X. And here you'll simply have Z. Okay. So yeah, I just had the slide to shall tell you that. So giving you a duality perspective, right? Two ways of making a sculpture. So if you have to carve out a sculpture, right? You can either, you can have some mold into which you put cast. Right? The murti, you put a cast into mold. That's how you create one definition of polyhedron. Right? You fill up the cast into the mold. The other definition is you chisel away. Right? You have some rock, you chisel away. You have a marble slab, you chisel away and create your murti. So the same thing is happening here. So this dual is now giving us a nice way of defining subdifferential. Okay, so this dual definition, because it's in max over max, this primal would have been very difficult for any arbitrary p. Sorry. Okay. So this is exactly what I wrote there. So now you can use this to again derive the subdifferential of one norm of X. We have done this before in terms of S, but now you can apply specifically and again try and derive. This is now we have a more generic tool. Okay. Now, the lasso problem, or if I have to compose all of these, right? The lasso problem, what we have done is we have taken 1/2 y minus x norm square minus lambda x. We wanted to compute the subdifferential of this. I've taken a simple case where the A has been set to 1. A has been set to identity, right? It's just y. How will you compute its subdifferential? The subdifferential of this we know. It's a convex hull. What is the subdifferential of the first component with respect to x? Yes. You know these compositions? Well, chain rule, you can apply chain rule also. Or you can expand y minus norm x whole square as norm y square plus norm x square plus 2 times or minus 2 times y transpose x, right? And then you can apply this rule, subdifferential of f1 plus subdifferential of f2. So what will you get there? The first term, norm y norm square will disappear, right? Norm x square will have a 2x, and y transpose x will have, or x transpose y will have x. Sorry, x. I'm no y. You'll have y. Okay. You'll basically have y minus x. Okay, so so x minus y. This will be just x minus y. The first term will be x minus y. Simply by applying subdifferential to be the sum of the subdifferentials. And the second term is what we saw earlier, right? Where you look at issue being at 0, and that's why we look at the convex hull. The one norm of x is basically the convex hull of all those SIs, such that SI is max at x, right? That's what we did here. So you see, now the calculus can be used to compute many subdifferentials. Okay, so this is the subgradient of f, is basically look like h equals x minus y plus lambda s, where SI is sine of xi. So basically SI is sine of xi if xi is not equal to 0. And SI is anything between -1 and 1 if xi is equal to 0. The same canonical figure which I had shown earlier, right? If you are any other place, you can just take it to be sine of xi. But if you are here, you have to consider that entire convex hull, which is if xi is equal to 0. You have to consider SI is in -1 to 1. This is basically the answer, right? So you need to go through this and make sure you are comfortable. I'll just quickly run through some more subgradient calculus. You can also do composition with vector valued functions. Composition, you remember this, if Qi is convex, P is convex and non-decrease in each argument, then F is convex. If Qi is concave, P is convex and non-increasing each argument, then also it's convex, right? What will you do in this case? So I'm not going to spend a lot of time. You need to try and solve it yourself. What will be the basic logic to compute subdifferential? Sorry? Chain rule, exactly. But you'll have to do a little bit more work. Now, what is the definition of subgradient? F of y is greater than or equal to f of x plus h transpose y minus x. What you'll have to do is use that h transpose y minus x in each argument. Okay. So you'll have to do something like this. Okay. I'm just showing you this. You'll have to do something like this. I'll leave it as homework, but you'll have to consider the case. For example, f of y is p of q1y qky, which is p of q1x, which is greater than or equal to p of q1x plus the qth component of h transpose y minus x. Okay. So you'll have to basically use this inequality, the inequality for subgradients, to compute or guess new subgradients. So imagine you had subgradients for each of those individual Qi's, for each of the individual P's. Now I want to compose. So you have the subgradients for the HQIs. You have subgradients for the P's. So you have to use both of these to come up with subgradient for the composite. Okay. So please make sure you do this as homework, because I don't think I don't want to spend so much time deriving it. But it's a very interesting derivation. It's not at all difficult. It is just algebra, simple algebra. Okay. So this is going to be homework problem. And mandatory. I mean, you have to spend time to understand this. I'll put the slides. And starting next class, we will, I think, now we are done with subgradient calculus. We should, we'll basically look at the, so this, there's a couple more actually, proximal operators, etc., which will not take time. But what I want to do is subgradients, how they are useful for optimization. So we'll move on to optimization next class onwards. So make sure you have brushed things up properly, because now we're going to use these left, right, and center for optimization. Okay. I'm going to leave some of this for you to read. I will upload the slides. Thank you.